So let's recall what is an orthogonal set. If you have set of vectors, we say those vectors are orthogonal when any two of the vectors are, if you pick up any two vectors from that set, when you take the dot product, that must be 0. Or in other words, any two distinct vectors from that set are going to be perpendicular to each other. What do we mean? Like inner product of v1 and v2 is going to be 0. So here is the definition we have seen. Right? Inner product of vi and vj will be 0 whenever I not equal to j. Suppose when you know that each vector is of length 1, then I can say that set is orthonormal. An orthogonal set where the length of the each vector in it is 1, I can say that is orthonormal set. Okay. So orthonormal, it means one more extra condition is adding here. You are having a vector of length 1. And then we studied some important properties of orthogonal matrices. We have seen the definition. And what the theorem says, when it is orthogonal, A into A transpose and A transpose into A, both will be identity. And you look at the definition. Definition of the orthogonal matrix is this. We say a square matrix is orthogonal when it is invertible and its inverse is equal to its transpose. It means A inverse is A transpose. Then we see how to construct an orthogonal matrix. You just start with any row or any column other than non-zero. Okay, so you start with any non-zero row or a column. Then with the help of that, you can actually construct an orthogonal matrix. First, you normalize the taken vector. Then you try to find the vectors which are perpendicular to the first one. And similarly, to find the third column, find a third column which is perpendicular to first and second column. That way. But here you should do one thing. You should make sure the length of each column is 1. And if you take an orthogonal matrix, its determinant is plus or minus 1. You can readily see the proof because you know the determinant of A into B is determinant of A into determinant of B. So using that result, you can find out the determinant of an orthogonal matrix is plus or minus 1. And the next thing is product of two orthogonal matrices is again an orthogonal matrix. So product is going to be orthogonal again, but when you take sum, is it going to be orthogonal? When you take two orthogonal matrices, what about their sum? We observed yesterday that need not be an orthogonal matrix because you are getting an extra term that is A transpose into B plus B transpose into A. Suppose if that extra term is equal to minus I, then I can say that the sum is also orthogonal matrices, provided this extra condition. Okay. And then we have seen constructing an orthogonal matrix. So we have seen how to construct it here. See, it is not just one matrix. You can construct infinitely many matrices where this one has a first column. Okay, I took here 4, 0, 1. You could have started with something else. Okay, you could have started with let's say 8, 1, 0. The second column you can take it as 8, 1, 0. So that creates another orthogonal matrix. Yeah. What is it you remember when you look at this matrix? Which kind of matrix is this?
Permutation matrix.
Permutation matrix. Good. So this is a permutation matrix. We have seen that every permutation matrix is going to be orthogonal. Okay. And if you want its inverse, that is simply A transpose. Of course, that is the definition of an orthogonal matrix. Okay. So if you are asked to construct a matrix of big size which is orthogonal, you can simply write a permutation matrix of that size. Yeah, then I asked you to solve these problems. Any questions or doubts in these problems? Definitely there will be doubts if you tried it. If you haven't done, please try it. Okay, so let us come to this today topic. So I hope you came to know what are orthogonal matrices and its properties, the basic properties related to the orthogonal matrices. Now, let us try to take a matrix with complex entries. So the moment you come to the complex entries, for example, I am taking C cross C. What I mean, I am taking C2. So here all elements are ordered pairs where each element is coming from C, complex number set. Let's say A plus IB and C plus ID. So if you want to write it as a matrix, this is how we'll write A plus IB and C plus ID. Okay. So now the question is, how do we define an inner product here? So in R2, we defined a dot product. So the dot product is, you know how to take dot product of two elements. Let's say A1, A2 and B1, B2. So if you want to find dot product of these two, let me call the first one is A and the second one is B. So you can simply do this A transpose into B. So this will give you A dot B. That's what exactly A1 into B1 plus A2 into B2. Suppose if I have complex entries here, then what do you do? Let me say A1 plus I C1, A2 plus IC2 dot product with what else you need? You need, let me take B1 plus ID1 and B2 plus ID2. So here we need these conditions. The condition is when you take dot product of the same element, that has to be non-negative. It means either it can be 0 or it should be positive. And we know one more thing. When it is 0, when the dot product is 0, then definitely B must be 0. What I mean, when you take dot product of that element with the same element. Suppose if that result is 0, then definitely V must be 0. It means the length of V must be 0 only. Then only you can get V dot V will be 0. Right? So suppose if you take this dot product directly, so let me do one thing. Let me take 1 plus I dot product with the usual dot product. 1 plus I. So if you do it, what do you get here? 1 plus I whole square plus, you'll get I square. And let me do one thing. What happens if I take just 1 here and 1 here? So that I get 1 square here. Okay, plus I into I square. So you know this is 1 minus 1, you're getting 0. So these elements are not 0, but if you take the usual dot product, we are getting it as 0. So can it be an inner product? The operation what we define here, can it be an inner product? Hello. What is it? No, that cannot be, right? So this cannot be an inner product, correct? So now we'll modify a little bit. So we're going to modify this definition. I mean, the dot product when you have complex entries is modified a little bit. So here, when you take two vectors, let's say u and v, so if it is with complex entries, then their dot product is defined this way, or the standard inner product is defined like u transpose into v conjugate. Okay, so now we are going to take its conjugate. So now let me apply this definition. So when I take this dot product, so according to the definition, so I must write its transpose first. So the transpose of this is 1i, whereas the next one is conjugate. So that is 1. Conjugate of I is minus I. Now let me take the matrix product. So this is 1 square plus I times minus I, right? So this is 1 minus I square. But you know what is I square? I square is minus 1. So therefore 1 plus 1. So this is 2. Yes, it gives us the correct result. So when you take this, let's say this is v dot v, we are getting 2. It means the length of v is going to be root 2. Yes, we know that is correct, because if you have 1 plus I here, the position is denoted like 1 comma 1. Can I compare with this? C2 over C. No, it's not good. It's not good to compare like this. Because it will be complicated. If I take 1 plus I and minus, then we won't get it. Okay, so now it is a vector of length root. So that's what it says. Now the dot product we didn't get 0. And you can see when it is going to be 0. Let's see that suppose if I take A plus IB and C plus ID. So this dot product with the another guy is the same. A plus IB and C plus ID. So as per the definition, the dot product is defined this way here. A plus IB, C plus ID, this is transpose, multiplied with conjugate of this. The conjugate of A plus IB is A minus IB, whereas this is C minus ID. Okay, now this will be A square. Okay, let me write one step. This is A plus IB into A minus IB plus C plus ID into C minus ID. I hope you can see this is nothing but A square plus B square plus C square plus D square. So if you want this to be equal to 0, this is 0 if and only if when A, B, C and D all are equal to 0. Means you can see that dot product of the same vectors like v dot v is 0, the inner product of v and v is 0 if and only if v equal to 0. So we got that condition. Okay. So remember that when you are in a complex plane, we are going to take dot product this way, like u dot u or u dot v equal to u transpose into v conjugate. Okay. So the conjugate will come here. Right. Now I'll give you a task. The task is, I'll give you a vector in C3. Let's say, let V be a vector in C3. Okay. Where I'll tell you what is V. V is nothing but 1 plus I and 2. So this is what V. Now my question is, can you give me another vector in C3? Find U in C3 such that U is perpendicular to V, where I am taking the standard inner product on C3. The standard inner product is V transpose into V, like U dot V equal to U transpose into V conjugate. That's how it is defined. So keep it on paper and tell me what is the answer. So try to find a non-zero vector. So Swaroop answer is 1 I minus 1. Okay, let me check. So this is what I need to do. I need to take an element like A plus IB, C plus ID, and let me take X plus IY. So this is U. Let me assume this is U. So when you take U dot V, I want this to be 0. Instead of writing dot product, let me write it like this. Inner product of U with V must be 0. It means U transpose multiplied with V must be 0. Now in that case, U transpose multiplied with V, we can see that is A plus IB multiplied with 1 plus I. Oh my god, I should take conjugate. U transpose into V conjugate. So let me take conjugate, and this is plus C plus ID into I conjugate plus X plus IY into 2 conjugate. So when you do that, when you multiply them, what is it you get? Say I'll do one thing. It's A and B. You can take any arbitrary such that which this product will be equal to 0. So I'll do one thing. So to make it easier, initially let me take A equal to 0. Okay, I'll have some restrictions here. I want to find an element where A is 0 and B, no, let it be there, so that it will be IB into 1 minus I plus, and let me see if I take D equal to 0 here, let me see whether I can get success or not. So when D is 0, so I'll have only CI. So C into I conjugate is minus I. 2 conjugate is 2 only. So this is 2x plus I2y. This we want it to be 0. Now you try to write what is the real part and imaginary part clearly. So here 2x, which will come in real part, and I times minus I, that is minus I square, which is plus 1. So this will be plus B. So this is the real part, plus what is the imaginary part? I times, here I have 2y. If you want this also, you can take C equal to 0. But okay, let me take C only. So this is minus C, whereas here I'll have B. So you try to find a guy such that 2x plus B equal to 0 and 2y minus C plus B equal to 0. So you can have infinitely many solutions for this linear system. So you just tell me one solution. I'll do one thing. I'll take B equal to 0. Then in that case x will become 0. Then y must be equal to C. Okay. Let me have a simple life. So when B is 0, this implies x is 0. Now this implies 2y minus C equal to 0. Therefore, you just take C equal to 2y. So let me take y equal to 1. This implies C will become 2. Okay. Now let me write the element. Now U is going to be A is 0, B is 0. I have taken that way. Next, C plus ID, where C equal to 2. D is anyway 0. And whereas X plus IY, where Y equal to 1. So this is I. Yes. So this is one such element. You can find infinitely many such elements. But let me check whether I've done correct or not. So 2 times of I, that's okay, minus 2 times I, yes, you'll get 0. So therefore U is perpendicular to V. And let me check this answer. What is the answer here? 1I minus 1. 1I minus 1. So when you take the inner product, you'll get 1 plus I times minus I, that is minus I square, so which will be plus 1, and this is minus 2. We are not getting 0. Swarup, we are not getting 0 here. If you take 1I minus I.
Yes, that one incorrect. Try second one. Second one.
Second one?
First one is not perpendicular. It's incorrect.
Okay. So the second one, 1 minus 1 by 2. Okay. So if I take 1 minus 1 by 2, so this, you'll get 1 plus I, now plus I. Still I'm not getting it. Minus 1. I'm getting 2I.
It's a minus 1. The middle element also minus 1 minus 1 minus 1.
Okay. 1 minus. Okay, this is also minus here. Fine. Then you'll get minus here. So you'll get 0. So you can construct infinitely many elements. Okay, I have a lot of freedom here. I can choose A as my wish and B as my wish and similarly B as my wish. Right? Okay. Now, I hope you understand how to take inner product when you have complex entries. So we take conjugate. We transpose into U conjugate. So that is how we take. Now let us try to discuss what are unitary matrices. Suppose in real case we have seen, suppose if you take a matrix with real entries, let's say A is the matrix. There we have seen a matrix where the columns are orthogonal and the rows are orthogonal and each column is of length 1. So such a matrix we are calling it as an orthogonal matrix. That's nothing but A inverse equal to A transpose. So this is the definition for orthogonal matrix. Now if I have complex entries, let us say you have a matrix where the entries are coming from complex numbers. You have an n by n matrix where each entry is coming from complex numbers. Then so similarly here, can I discuss something like this? A matrix where the columns are orthogonal and each column is of length 1. Then what is the name we are going to give for that matrix? A matrix with complex entries where the columns are orthonormal. Let me simply say the columns are orthonormal. So in that case, how should I define this guy? Should I take A inverse equal to A transpose simply? So when the inner product is defined as transpose into conjugate, then definitely when you come here, so here we are going to take A into A conjugate whole transpose. Okay. I got a doubt. these two same? If I take V conjugate transpose into U, will it be same as this? No? V transpose U, when I take whole conjugate of it, so I'm going to get V transpose conjugate and U conjugate conjugate. So this is same as V conjugate transpose and this is U. So what I can say is these two are not exactly equal, but I can say that one element is conjugate of other element. So when you take conjugate of this guy, you'll exactly get this. Okay, you can see the proof here. V transpose U conjugate, whole conjugate will give you this. So suppose if you have a matrix. So let me construct a matrix first. Later I'll go to the definition. So suppose let me take a simple matrix I 0 0 I. So this is the matrix I'm taking. Here, if you take it as A, what is A into A transpose? Tell me. So this is identity matrix itself. I mean, not identity. I times the identity matrix. So this is same as I squared times, when you multiply identity matrix twice, you'll get this. Again the identity matrix. So the result is -1 0 0 -1. Okay. Suppose if you get A into A transpose equal to identity, then I can say that is a what is its name? Orthogonal matrix. We say it is an orthogonal matrix, but here we are getting minus into identity. But if you observe that it is with complex entries, so you better take conjugate transpose. So when you take conjugate transpose, let's see what happens. So this is I 0 0 I, and this is minus I 0 0 minus I. So that's equal to minus I square 0 0 minus I square. So that will be 1 0 0 1. So you'll exactly get the identity. Okay, so therefore here we got this A into A conjugate transpose equal to identity. Of course, this is the inner product if you observe. So if you find any such matrix, so that matrix we are going to call it as a unitary matrix. Like how we have studied symmetric matrices, skew-symmetric matrices, and then Hermitian matrices, skew-Hermitian matrices. Similarly, in real case we study orthogonal matrices, whereas in complex case we study unitary matrices. Okay, so for orthogonal it is just A into A transpose equal to identity, whereas for unitary matrices A into A conjugate transpose is equal to identity. It is true in both ways, A into A conjugate transpose and similarly A conjugate transpose into A. Both must be equal to identity. But we have a notation for A conjugate transpose. The notation is A star transpose conjugate. So in future we simply write it like this: A into A star equal to A star into A equal to identity. Okay. So this is the definition for unitary matrices. Unitary matrix. A square matrix A which is with complex entries is said to be unitary if A inverse equal to, of course that A must be an invertible matrix, and A inverse equal to A star. For orthogonal matrix, the definition is A inverse equal to A transpose, whereas for unitary matrix, A inverse equal to A star. Okay, I'll do one thing. I'll give you a matrix here. Tell me whether it is unitary matrix or not. I don't say this is an example. I'll just give it as a problem. A equal to I minus 1, and this is 1, whereas this is I. So my question is this: is A unitary? Yeah, there are some other examples here. 0 minus 2i minus 1, 2 minus 1, 2 minus 2 minus 1. Good. Now my question is A unitary matrix? What are you going to do? Are you going to take A into A star? Are you going to check that? No need of checking that if you observe, because we know what is orthogonal matrix. From that only we got this what is its name, unitary matrix, right? So in an orthogonal matrix, each row is of length 1. Similarly, in orthogonal unitary matrix, if either you take a row or column, that should be of length 1. First you check that. So look at the first column. So the first column is 1i. What is its length? What is its length? So if you want to check its length, this is what you have to do. I1 multiplied with conjugate minus I1. What is it? This is 1 plus 1, you'll get 2. So the length is root 2. The length is not equal to 1. So this cannot be a unitary matrix. So no need of writing the transpose conjugate and multiplying A and A transpose. No need of doing that. You can simply check with this.
The inverse కూడా exist అవటం singular matrix.
Is this a singular matrix?
I think it is.
Okay. So what you have seen is the determinant. The determinant is I square plus 1, which is 0. Yes. And let me see, if it is singular, since it is a 2 by 2 matrix, the second column must be obtained using first column. So can you tell me how to obtain the second column using the first column here? Your observation is correct.
Into I, first column into I.
First column into I. Let me see. So I1, if I multiply this with I, so what I get is I square, and here I, so I get minus 1I. Exactly. So this is a this is a singular matrix. So if it is a singular matrix, we cannot say it is unitary, because in a unitary matrix, the definition itself is it is non-singular and A inverse equal to A transpose conjugate. Okay, yes. So this is not a unitary matrix. Therefore, the conclusion is A is not unitary. Okay. Now this time let me give you another. 1 plus I, 1, this is I, whereas this is 1 minus. What is your answer? Okay, my question is this: is A unitary? What is your answer? Yes or no? Oh, interesting. Length of the first column is 1. Let me check.
I think it's root 3.
1 plus I and I. This is what I have taken. So let me take the conjugate and the conjugate, and I need to multiply with this. 1 plus I. Okay. So 1 plus I into 1 minus I. So I get 1 plus 1. That's the first thing. Plus I times I conjugate. So that is minus I square, which is plus 1. So this is 3. We are getting 3, no? Be careful, don't get confusion. The first column is this, C1. If you want the length of the first column, this is what you need to do. Square root of C1 inner product with C1. And the inner product is defined this way. C1 transpose multiplied with C1 conjugate. Okay, where C1 transpose is this, that is 1 plus I, whereas C1 conjugate is 1 minus I and minus I. Okay, so when you take the multiplication, you'll have 1 plus I into 1 minus I and minus I square. So you'll get 3. Under root. So root 3 is the length. So definitely A cannot be a unitary matrix. A is not unitary, that's for sure. Okay. Okay, let me give you one more. 0, I, 0, 0, 0, I. This is I, 0, 0. What do you think? Is A unitary? You can write what is A star. Transpose, conjugate transpose, right? So 0, 0 minus I, whereas the next one is minus I, 0, 0, 0 minus I, 0. Okay. So let me see what is A star into A. So A star into A. So this is 0 plus minus I square plus 0. So minus I square, you know, that is 1. So the next one, this will be 0. This is 0. And next you can see that 0, 1, 0. Next 0, 0, 1. Okay, so we got an identity matrix. Therefore, since A star is I, therefore we can conclude that A is a unitary matrix. Okay. Now you do one thing. So you have a homework. So the homework is this. you try to construct a unitary matrix. So here I have given a simple example, but not like this. You try to construct a unitary matrix where most of the entries are non-zero. So be clever in constructing. I need most of the entries as non-zero entries. Okay, when I am doing, I am making my life is getting easy, right? I am making my life easy. And when I give problem to you, I am making your life difficult. Okay. So construct a unitary matrix of size 1:2, and similarly the same question, another one is of size 3. Okay, so take it as a homework, try to construct. Okay. Now let us come to the properties of unitary matrices. So the same, whatever we have studied for orthogonal matrices, so the same we'd like to see. Now if you take a unitary matrix, what is its determinant? First let us recall what are the properties we studied earlier for orthogonal matrix. What is it? Let me check. I think we started with determinant only here. Anything else? Yeah, that's it. One thing is determinant we have seen, another one is product, and then we discussed about sum. Okay. So my question is this: if A is a unitary matrix, then what is the determinant of A? Can you say something about determinant of A? So if it is orthogonal, we said it is plus or minus 1. If it is unitary, is it going to be plus or minus 1 again? So here, let's verify what is it. So we know if A is unitary, we know A inverse equal to A star. This is the definition. And we know one more if and only if condition, that is A into A star equal to A star into A, which is equal to identity. Now let me take the determinant of this matrix, determinant of A into A star, that's equal to determinant of identity matrix. We know from the properties of determinant, we can express it as determinant of A into determinant of A star. So determinant of identity matrix is 1. Yeah. So we know determinant of A transpose is same as determinant of A. But what happens if you take conjugate? Is it going to be same? Now you have to be very, very careful. We are taking a matrix with complex entries. So earlier you have a matrix with real entries only. So we know x square is equal to 1 when x equal to plus or minus 1. That's it. But here, I know the entries of A are complex. Okay. And the determinant of A, that also, it can be a complex number. See, for example, if I take this matrix 1, 1, 1, I, what is its determinant? So its determinant is nothing but I minus 1. So it is a complex number. So when the entries are complex, the determinant also can be a complex number. Okay. So there are few things we need to think about. What is determinant of A star? Is it going to be determinant of A or not? That we need to think. But we know one thing, determinant of A transpose is same as determinant of A. So only thing you need to make sure what is the determinant of A conjugate and the determinant of A. What is the relation between them? This we have to see. And do you remember the definition of determinant? The definition of determinant is this: summation like A1, I1. This is A2, I2, A3, I3, and so on, AN, IN, and minus 1 to the power of that is the sigma, where sigma is the sign of, it's not sigma, or let me take sigma into this, where sigma is going to be sign of the permutation, whether it is even or odd. Okay, so here when you take conjugate, what you are going to do, you are going to take conjugate of each and every element, and we know from complex numbers z1 into z2 conjugate is same as z1 conjugate into z2 conjugate. So then you can take whole conjugate of this. So then the determinant of A is same as determinant of A conjugate is same as determinant of A whole conjugate. Okay. So now for determinant you need to take the conjugate. So now I can say one thing, determinant of A star, which is same as determinant of A whole conjugate. So let me see that this is determinant of A into what I have is determinant of A conjugate. You can write it as whole conjugate. That's equal to 1. So you need to think about a number. If you take x plus iy, okay, let's assume the determinant of A is x plus iy and the determinant of A conjugate is x minus iy. We want this to be equal to 1. Then what do we have? X square minus y square equal to 1. Sorry, x square plus y square equal to 1. So what is x and y must be? So can you say something now? Can you conclude something? Are you sure that it should be plus or minus I? So length is I. What do you mean by length is I? Okay, length is 1. So this is what I got, sir. If you take a unitary matrix, when its determinant is x plus iy, then x square plus y square must be equal to 1. It means what? Is that I and minus I?
1 plus I.
1 plus I?
Or minus 1 plus I.
Okay, you're saying plus or minus 1 and plus or minus I.
Yes, sir.
If any two numbers satisfy that circle equation.
Yes. Circle equation, it means that that's a unit circle, right? So it can be any complex number which lies on that unit circle. Okay. So what I can say is the determinant of unitary matrix, when you take its absolute value, that is going to be 1. Yeah, I plus or minus I, they can be the determinant of this unitary matrix, that is for sure. But it says that we have something more. Not only just plus 1 minus 1 I minus I. We have something more. That's what it says. So the final conclusion is this: if A is unitary, then the absolute value of determinant of A. Be careful, I am not saying the determinant of A is 1. I am saying absolute value of the determinant of A is 1. Okay, or in other words, you can say determinant can be any number which lies on the unit circle. For example, I'll give you one example. If you take 1 by root 2 plus I by root 2, does it lies on the unit circle? You can observe that x square plus y square equal to 1. So this can be determinant of this unitary matrix. Okay. So this is one thing we can observe about the determinant of a unitary matrix. And next, and I'd like to check the definition. The thing is, I told you the determinant of A conjugate, that's going to be determinant of A full conjugate. So let me just verify with one example whether it is true or not. We have seen the direct proof, but still I'd like to verify. So if I take just I1, 1, 1, what is its determinant? That's I minus 1. Whereas when you take conjugate, A conjugate is minus I1, 1, 1. So that's going to be minus I minus 1. So let me take, so the determinant of A whole conjugate, so that's going to be minus I minus 1. Yes, we can see that these two are equal. So that is determinant of A conjugate. We got it. It is same as the determinant of A whole conjugate. Okay. Now I'll ask you a question. Suppose A is unitary. Let's say A is a 3 by 3 matrix. And A is unitary here. Then the determinant of A, let me say which of the following number can be determinant of A. Okay, so option A, let me take 1 minus I, and option B, root 2 minus I, and C, I, and option D, minus 1, and option E, more than one answer can be correct. Okay, and this is minus I and F. Let me take 1 plus, let me take a nice numbers. The nice numbers are, okay, got it, 4 by 5 plus 3I by 5, G 4 by 3 by 5, 3 by 5 minus 4I by 5. Okay. So tell me, which of the following options can be a determinant of a unitary matrix? So therefore, option A is wrong, B is wrong, C, D, E, F, G are correct. right? So the next thing, let's say if A and B are unitary. Let A and B are unitary matrices of same size. Where A is a matrix of size n by n, B is a matrix of size n by n. Then, what can you say about A into B? Is it going to be unitary? What is it? It can be unitary. Don't say can be. You say is it or not. That's it. AB, will it be unitary? Let me check. So what we know is A inverse is A star and B inverse is B star, or in other words A into A star, that's equal to A star into A, which is identity, and similarly the other. B star into B, that is identity. Now let me check AB into AB star. So that is AB into B star A star. So that is A into B star into A star. So this is nothing but A into identity into A star. This is going to be A into A star. So this is I. That's it. So therefore AB is unitary. When A and B are unitary, then their product is also a unitary matrix. Okay. So that's it. So the most important thing you need to observe is, if you take a unitary matrix, its determinant, absolute value of the determinant is 1, not the determinant is 1. What do we know is, when you take determinant, that will lie on a unit circle. It means you will get an x plus I y where x square plus y square equal to 1. So I can be a determinant, minus I can be a determinant, 1 can be a determinant, 1 by root 2 plus I by root 2, that is also can be a determinant of a unitary matrix. Okay. So you should understand it like this, like symmetric Hermitian, like symmetric in real, Hermitian in complex, and similarly skew symmetric and skew Hermitian. Similarly orthogonal and unitary. Orthogonal means you will only discuss with real entries, whereas unitary we will discuss with complex entries. When you say complex, they can be real as well. Okay. So I'll stop it here and let me know if you have any questions or doubts. Okay, then bye. We'll meet in the next.